Hello everyone. In this video, we will talk about the matrix notation of multiple linear regression. So in fact, MLR is much more manageable with the matrix notation. Okay. So consider a model with k independent variables, which means I have beta 0, beta 1, right? Beta k, different beta values and corresponding x values, and many observations. Okay, so from the previous example, remember I have beta 1, beta 2, and beta 3. Remember, so I have three betas. The first one was the meat, the percent of meat. The second one was vegetables, and the third one was what was it? It was spices, right? And I have 13 many examples. So I just cooked a meal with different percent of meat, vegetables, and spices, and I just record a Y1, so the like rate of that food. And then I just cook another meat, okay, with different values of meat, vegetables, and spices. Well, I just record that its like rate, which is Y2. And I have how many? 13 many different Y values, okay? Then the model has the following form. So the ith observation, okay, remember I have 13 many i's, is equal to beta 0 plus beta 1 x1i. Again, remember we said that we have two indices now because I have multiple x's. Okay? So beta 2 beta k xki plus the error term epsilon I. And still we have, this is normally distributed, this is our assumption with constant variance sigma squared. Okay? Well, in fact, this model represents any equations. Okay? Any equations. Why is that? Again, just go back for the food like rate example. I have the first group y1, then y2, I have y13. Okay, so I have 13 many equations here, right? And it can be expressed as uh, as this notation. Okay, so I have y equal to x times beta plus epsilon. So what is y? Y is the n times one vector. So what does this mean? Y is something like this. Okay, y is I have y1, y2, y, n observations. This is equal to, well, this is the vector x. Okay. Um, Let me just do it like this. So this is n times k plus 1 matrix. Okay. So what does it mean? Again, it has, so 1, 2, You have n many rows here. So this is the number of rows. Remember, this is the number of rows. And this is the number of what? This is the number of columns, right? So k plus 1 column means that what we have, remember, beta 0, beta 1, beta k. So you have k plus 1 betas. That's why you have the k plus 1 rows. And you have k plus 1 columns, and you have n rows because you have n many observations, right? So this is k plus 1 vector. That's simple. We will see the x vector, okay? I will just write beta here. This is beta 0, beta 1, beta, let's say, beta k, and plus epsilon. Epsilon is symbolizable epsilon 1, epsilon 2, epsilon k. Okay, so epsilon n many observations, right? Okay, so this is what we have. So this is my x. So sorry for this. This is 1. So I have a space here, right? So it is something like this. 1, x1, 1, x2, 1, okay, x2, 1, xk1. So in fact, let me just do this. Let me just do this using our example, okay? So using our example. So our example was we have three betas, right? So it will be something like this: 1, x, 1, 1, x2, 1, x3, 1. Okay, and the second line x 1, 2, sorry, 1, 2, x2, 2, x3, 2. Okay, that it goes like this: 1, x1, what? Which observation is the 13? X 2, sorry, 2, 13, x not that, sorry, x3, 13. Okay. So, well, this is what we have in our example, right? Okay, just like this. So what you do is, in fact, when you just multiply this with beta, right? Because you have x times beta, right? This is what you have. So what you do is you just take this part, okay, and just transpose it. Remember how you multiply the matrices with vectors. You just multiply, just take the transpose of this, which means you will have something like this. Let me just write it here. 1, x1, 1, x2, 1, x3, 1, and with the corresponding beta 0, beta 1, beta 2, and beta 3. And we just multiply it with this, okay? So in the end, you will have beta 0 plus beta 1 x1 1, right? Plus beta 2 x2 1 plus beta 3 x 3 1, right? And this is equal to what? This is equal to y1, right? Plus what? Plus epsilon 1. So I just make it a squeeze here. So, okay, let me just write it here again. So y1 is equal to beta 0 plus beta 1 x1 1 plus beta 2 x2 1 plus beta 3 x 3 1, right? Plus epsilon 1. So what does it mean? It means that, well, this is the meat percent of the first food. This is the vegetable percent of the first food. This is the spice percent of the first food. And how about this? Let me just write the last one, y13. Okay, let me just write y13, not here because it just comes to here. Let me just write it here, y13, that's equal to beta 0 plus beta 1 times what now? x1, 13, okay? Beta 2 times x2, 13 plus beta 3 times x3, 13, right? And what is this? This is the meat percent. Why meat? Because I have one here. Meat percent of the 13th food, okay? This is the vegetable percent of the 13th food, right? And this is the spice percent of the 13th food, okay? Great. Okay, so this was our example, right? And this is our X matrix. Okay, I have 174, it's here. 5.30, it's here. 10.80, that's here. So let's say 632 here, 542 here, 940 here. Okay, and the last one, 170, 530, 820, 170, 530, 820 there. So why do we have here this one? That's because, well, so this is x1, sorry. Um, so this is x1, right? Which corresponds to beta 1. This is x2, which corresponds to beta 2. This is x3, or which is multiplied by beta 3. And this is, in fact, we can say x0, right? This is the x0 independent variable, which is multiplied by beta 0. So x0 is the same for all of the variables, okay? Because you have 1, 1, 1, 1, 1 here. But the other x's, x1, x2, x3, they are just changing. So you just put different percent of meat and spice and vegetables to each meal. But it turns out that, well, this is 1, up to here, this is 1 for every food. So what do we do here? Although we didn't show it in our notation, okay, although we don't write here x0, right? x1, that we have beta k xk, we just put this x0, okay, into this matrix notation to make it possible to calculate the correct values of b0, b1, bk. Okay, so, well, this is my true hypothetic regression line, right? Y is equal to x beta plus epsilon. But I don't know the exact values of beta, right? So what do I do is I just find an estimate for them. Okay? So what are the estimates? Well, it's a vector, which is a k plus 1 vector, b0, b1, bk. Okay? So y hat is equal to x times b, right? And again, what is y hat? This is the estimate of what? This is the estimate of that particular x value. Okay. And the sum of squares, remember, it was yi minus yi hat. Okay, yi minus yi hat squared. We just sum them up. So it's exactly the same, but so the difference is, remember, yi hat, it's now you have b0 plus b1x1 dot bk xk. Okay. And the second thing as well, with the matrix notation, you can just show this as a C instead of the summation. You can just show it by y minus y hat transpose. So this is transpose, right? This is transpose, right? Minus 5 minus yi hat, which is also equal to, instead of y hat, I just put x beta, right? And this is what you have instead of in terms of, sorry, the sum of the error sum of squares, right? Well, if you just take the partial derivatives, well, I don't get into the details, but well, this is what we call the least square equations. So these are the equations that you solve to find the value of B, and B turns out to be equal to x transpose x inverse times x transpose times y. Okay, so this is the value of the estimates for B. Again, what is this? This is the x transpose x. So this is somehow an x squared, and this is the inverse of this, okay, times x transpose times y. So in our case, in our example, the estimated regression coefficients turns out to be, well, remember in the Excel, we have this as well. This is 39, 1.0161, and so on and so forth. In fact, this is the result of x transpose x inverse times x transpose times y. So at the comfort of your home, you can just make this multiplication, okay, to see that whether it's really equal to this one, right? So the estimated regression equation is equal to this thing. So what is this? This is, remember, this is B0, this is B1, and this is B2, and this is B3. Okay, so this is your estimated regression line. So what, again, what does this y hat gives? It just gives mu of, so this is this is an estimated for mu y given x, right? Also, you can just use this to make a point estimate, okay, to make a point estimate for this value. Okay? So, for example, if you are just using, I don't know, 10% meat and 2% vegetables, right, and 5% spices, if you just put it here and just multiply with the coefficients there, you will find the point estimate of the like rate. Okay? So this x transpose x inverse, well, that's a special matrix. It just forms the variance covariance matrix of the estimates. Okay. So the variances of the estimated regression coefficients, which are the BIs. So, okay, so we are talking about sigma squares of BIs, right? The sigma squares of BIs. They are given by the diagonal elements of this matrix multiplied by sigma square. And the off-diagonal ones, so what I mean by this is, so the diagonals right here, the diagonals just give you the variances, and the off-diagonals here, let me just make this as this. Sorry. Okay. The off-diagonal elements just give you the covariance. Okay. So in our example, x transpose x inverse is equal to this one. So what does this mean? Variance of B1 is equal to 0.009 times sigma square. You see this? And the other one is 0.017 times sigma square. And variance of B3 is 0.089 times sigma square. And for example, the covariance of B1 and B2, okay, B1 and B2 is equal to what? 0.02 times sigma square. Okay, so these are the covariances of B1 and B2, right? So the diagonal elements, so this is the variance of B0, right? Not the variance of B0, but this is the coefficient to find the variance of B0. So this one multiplied by sigma square give you the variance of B0. Okay. So of course, X transpose X. So this is a squared matrix, and it's a symmetric matrix, right? So once you know here, once you know the upper triangle, that is what they call in matrices, then you know the lower triangle because they are symmetric. Okay. Well, that's good. Okay, that's fine. But how about sigma square, right? Do we know sigma square? Of course. So remember, in the simple linear regression, what was the estimate for sigma square? It was a square, okay, which is found by the mean square error, which is also equal to SSE divided by n minus 2. Why it was 2? Because you have what? You have beta 0 and beta 1. You will estimate two parameters. So what do you think to see here? So what do you expect to see here? Right? Just try to think by stopping the video. What do you expect to see here in terms of an estimated for sigma square? Okay, so the estimated for sigma square is again a square, of course, this is what we call. This will be again MSE, and this is also equal to SSE divided by now, not n minus 2, but this is equal to n minus how many k's we will estimate? Well, beta 0, beta 1, beta 2, and beta 3. So you have 4 betas, right? This is n minus 4. In general, this is equal to SST divided by n minus k plus 1. Okay, so because you have beta 1, beta 2, and beta 3, that's why we have k here plus 1. This is what? This is beta 0. Okay, and this is what? This is an estimator for sigma square. That's the estimator for sigma square, which is what again? Which is equal to s squared. Let me just contract it here. This is equal to s squared. Okay, let me see. Right, exactly that's what we have. S squared is equal to SSE divided by n minus k minus 1, or this is n minus k plus 1. Okay, where SSE is equal to e squared, and remember what is error squared? That's yi minus yi hat, and again what is yi hat? That's equal to b0 plus b1, let's say x1 1, right? Not I, let's say b2 x2i plus b3 x3i. Okay, that's why what we have in terms of yi hat. Okay, well,